So far, we learned logistic regression and how to estimate, how to apply the Newton's methods to get better, faster algorithm estimations for the logistic regression. So by far, we learned several machine learning methods for classification, namely the linear discriminative analysis, and another one is logistic regression. So I would like to give a short summary to give you a summary of the pros and the cons for each of the methods. So the advantage of the linear discriminative analysis, okay? So for well-separated classes, okay, for well-separated class, LDA is more stable. Okay, and the logistic regression is not stable. Regression not stable, is unstable in this case. Is more is more unstable. It's because if you have the data more like if you have two class, for example, we have the blue dots here labeled as 0, and we have the red dots here. If they don't have any like overlapping data point region, so logistic regression sort of does not know how to fit the data. It's more unstable in this sense, but linear discriminative analysis is more stable in this case. Okay. So another advantage is for multiple classes problem. Class problem. It's relatively easy. LDA is relatively easy. And elegant to apply. You just fit the multiple for each class. You fit a normal distribution and then compare which one gives you the higher decision function value. So it's easier to generalize LDA to multiple classes classification case. On the other hand, logistic regression you need more work. Needs more work to generalize. Actually, there is a name called softmax. Regression. If we have time, we will also go over the softmax regression later. The last one is LDA. Is slightly more accurate. Give you more accurate classification if data follows normal distribution. Because it's also called Gaussian discriminant analysis, right? So the first step, you assume your data generated from the normal distribution. If that's the case, LDA perform better, especially when sample size is small. Okay. And also about logistic regression. Okay. Logistic regression more emphasis on the decision boundary. So give more emphasized. Boundary. Okay. Always separates linearly separable points. Okay, so correctly classified points far from the decision boundary have a small effect on the logistic regression, but a bigger effect than they have on the support vector machines, where the misclassified points far from the decision boundary have the biggest effect. Maybe I'll give you a chart here. For example, this is the data points here. We have a class labeled cross, and we have another class labeled as circle, and the middle point give you the logistic regression decision boundary. Regression decision boundary. Okay, and the on the right hand side it gives you the decision boundary given by the linear discriminant analysis. Okay, as we can see, actually this case is linear separable, although they are very close. You can see this logistic regression works perfectly for this case. But there's no misclassification cases for the if the data is linear separable, there will be no misclassified points. But on the other hand, and also the so this logistic regression gives more emphasis on the boundary points, so that it does not cross the decision. Try his best not to cross the decision boundary. But on the other hand, for the LDA, you can see there are a few points. For example, this point is cross boundary, and there are some circles cross boundary too. So LDA give all points equal weight. When fitting the Gaussian distribution, okay, but logistic regression give more weights. to boundary points. So weighting points according to how badly they are misclassified is good for reducing the training error, but it can also be bad if you want to stability or insensitive your bad to the bad data. Okay, so that's a little bit differences between. There is another point that for the logistic regression, which is good. It's more robust for the because linear Gaussian discriminant analysis assume the data follows normal distribution, but if the data doesn't follow normal distribution, logistic regression may be preferred. Okay, so it's more robust. On some non-Gaussian distribution data. Distribution data. Okay, for example, if data is skewed, data is skewed or bimode. And also the third advantage is naturally fits labels. Between 0 and 1. Okay, so usually if you want to find the probability based on something, maybe it's naturally to apply the logistic regression. For example, predict the probabilities. Okay, last part about one important tools will be commonly used to evaluate your classifier is a tool I'm gonna talk about next. It's called the ROC curve. ROC curves. So people can use ROC curve to evaluate how good your classifier is. Maybe let me give you the last plot. Actually, this ROC curve is called the receiver. This ROC stands for receiver operating characteristics. Okay, which is for some historical reason, but people just use the name. There's I think it's originally not. I don't like this name, but this is ROC curve. Is people use this name for historical reason. Okay, so ROC curve is a way to evaluate your classifier after it is trained. So a tool graph to evaluate your classifier after it is trained. Okay, It is made by running the classifier on the test site or validation site. So we obtain ROC curve is obtained by running classifier on test data set or validation data set. So what's the difference between test and validation? Test means some new future data. You suppose you do not have label, okay? No label. No label. Validation set is part of your training data set. Your training data set. Here you have label. You just want to, we want to check if our model works good for future data, but we cannot check that in general. So we want to divide some part of the training data as our validation data set, so that we can have the label on the validation data sets, and then we can check the performance of the classifier. Okay. It shows the rate of the false positive and versus true positives for a range of settings. Okay, so remember there are a few cases, right? If you classify the data for the classification, maybe let me draw you a chart here. So suppose about the COVID test, okay, COVID test. Okay, so there are some truths. Truth is you no COVID, and or you got COVID, and the test shows, or the classifier tells you you get a negative result or positive results. Okay, if you don't have COVID and the test shows you negative result, you are good, right? But if you don't have COVID, the test shows positive result, that's an error. That's error. So this is called false positive. Okay. Also, if you got COVID and the test result shows you got COVID, which is correct, so this is called true positive. On the other hand, if you got COVID but the test failed to detect it, this is another false case, right? It's called false negative. Okay. So ROC curve has two axes. So first is called the false positive rate. So on the x-axis, the label is called false. Maybe I will write using different colors. False positive. False positive rate. So which means how much percent of the cases with negative, but it's classified as wrongly classified as positive. Okay. On the horizontal axis, this represents the true positive case. So which means the percentage of the true positive cases classified as positive. This is also called the sensitivity. Okay, and and we can for the logistic regression or the LDE, we can adjust the decision boundaries by changing the knob, right? So by changing the. So you go to this direction, go to this direction, you adjust knob of the classifier. Okay, for example, remember in the logistic regression we have that logistic regression curve. Where I think last class we gave the logistic regression curve, I believe, if I remember correctly. Oh yes, here, right? So we can use 0.5 as a knob, right? Or we can use 0.2 as a knob, or we can use so if we use 0.5, which means if our logistic decision boundary Wxi is below 0 or above, after you apply to the logistic transformation, if it's above 0.5, you classify it positive, and below 0.5, you classify it negative. So we naturally choose this 0.5, but actually we can change this knob. We can change it to 0.2, 0.1, or even 0. 0 means we classify all the cases to be positive, right? Okay, so by changing the knob, we can get this. We can, for each of the knob, we can get a class of the classifiers, right? And maybe let's look at clearly what's inside here. Suppose now we use, let's say, 0.4 as a knob. Suppose here we use 0.4. So suppose, say, knob is 0.4. Okay. So the x-axis, this is the false negative. Okay, we have the chart here. So the distance between this y-axis to this point, this is called the false positive rate. Okay, this is the scale of the x-axis, and once subtract this one is called the true negative rate, right? 1 minus false positive means equals to true negative rate. True negative rate is called a specificity. True negative rate equals to 1 minus false positive. Okay. And this distance is sensitivity. So this is the sensitivity. Okay. Sensitivity means true positive rate. So the higher the better. We want higher sensitivity, and we want a lower false negative rate. So if you have a classifier more to the up left corner, the classifier is better because you have lower false negative rate and a false negative rate. I think this chart is very good. So 1 minus the false negative rate is the sensitivity. 1 minus false positive rate is called a specificity. And we can also have the two extreme case. Okay, so this means a knob, you choose a knob that classify all the cases with negative. You always classify as negative. And this one you always classify as positive. And we have also the diagonal line. Diagonal line means random classifier, which means you do not do anything, you just flip a coin. And if the coin turn up with head, you choose positive. With tail, you choose negative. So which means you should at least, your classifier should be above this diagonal line. Should be better than the tossing the coins. Okay, so this is called ROC curves. So ROC curves Up right corner. Okay, I think that's so in practice, the trade-off between false positive and false negative is usually negotiated by choosing a point on this plot based on the real test data set, and not by taking the choice of the threshold that best in theory. Yes, because if you change the knob, you may get a lower. If you change here, you may get a smaller. For example, if you get here, your classifier choose a knob here, you could get a lower false positive rate, but you get a large false negative rate. And think in practice, we want to find a optimum point that such that both false positive and false negative is smaller. Okay, I think that's all I want to talk about today. Thank you.